When a pulse of a traveling wave strikes a rigid boundary, it gets reflected. An echo is one of the simplest examples of this phenomenon. If the boundary is not completely rigid, or if it is an interface between two different elastic media, a part of the wave is reflected, and a part is transmitted into the second medium. Reflection of waves follows the laws of reflection, which are similar to the laws of reflection of light. To understand the phenomenon of reflection of waves, let us perform two simple activities. In the first activity, the left end of a string is fixed to a rigid wall. In the second activity, the left end of the string is tied to a ring which can slide up and down without any friction on a rod. A single pulse is generated at the free end of the strings. In the case of the first activity, the pulse, on reaching the left end of the string, encounters the rigid wall. The pulse applies an upward pull on the wall, and the wall applies an equal but opposite downward pull on the string, obeying Newton's third law of motion. The downward pull by the wall on the string generates a pulse which travels in a direction opposite to that of the incident pulse. As there is no displacement of the particle at the junction of the string and the wall, the incident and reflected pulses have opposite signs and cancel each other at that point. Due to this phenomenon, the reflected pulse has a phase reversal or a phase difference of pi or 180 degrees. In the second activity, when the pulse reaches the end of the string, it pulls the ring up. As the ring moves up, it pulls the string, producing a reflected pulse with the same sign and amplitude as the incident pulse. In this process, the incident and reflected pulses reinforce each other, creating maximum displacement at the end of the string. The reflection is without any additional phase shift. Let us now express